So we were talking about splitting fields. I had almost finished. There's one more thing that I wanted to see. What happened? Here it is, sorry. So we were talking about splitting fields. So this is just the smallest possible field extension of a field K over which a certain polynomial splits. We had studied this. Now, like in the case of simple algebraic extension, I want to talk about the extension of field isomorphisms to splitting fields. So if you have an isomorphism between two fields and you have a polynomial with coefficients in this one field and you apply the isomorphism to the coefficients of the polynomials, you can compare the splitting fields of these two. And so the claim is that an isomorphism between the fields will give us an isomorphism between corresponding splitting fields. And this will be important for us. In particular, it will also show that splitting fields are unique up to isomorphism. So up to K isomorphism. So let me state that. So the following theorem. So this is extension of field isomorphisms to splitting fields. So let small phi from K to K prime be a field isomorphism. And let f be a polynomial with coefficients in K, say non-constant. And we put f hat to be what I had called phi star of f. So that means we apply this isomorphism to the coefficients of f. It will be polynomial with coefficients in K prime. So I take the splitting field, or a splitting field of f over K. And a prime is splitting field of f hat over K prime. So then there exists isomorphism which I call, say, large phi from L to L prime restricted so K so we have an extension of our original isomorphism to the splitting field of the polynomial, where obviously in order to make sense of this we have to transform it, the polynomial to the other field. So in particular, we can apply this to the case when K is just the identity, that phi is just the identity of K, then it says the splitting field is unique up to isomorphism. So let L prime be splitting fields of a polynomial f in Kx over K. Then there exists a K isomorphism phi from L to L prime. So splitting fields are unique up to K isomorphism. So note that the statement here is weaker than the statement we had for simple algebraic extensions. For simple algebraic extension, we said precisely what the extensions are. There is a unique extension for every root. So if you take, say, if I do it in this case, if I take a root of the minimal polynomial, so if I have a simple algebraic extension, I look at the minimal polynomial, there's precisely a unique extension of the isomorphism which sends one root of the minimal polynomial possibly to another one. Here we have no kind of, we don't know how many extensions there are, we know that at least one. And that actually is important. If we knew precisely how many there were, then Galois theory would be very easy. But we don't. So now we have to prove the theorem. So we make an induction over the degree of the field extension. So if one, then we have then K, L is equal to K, and thus L prime is equal to K prime. And so our large phi is just phi. Okay, so it's, this case is trivial. Now we assume that the degree is positive, I mean it's bigger than 1. And we want to make this induction, so we have to reduce to a smaller degree of the field extension. And we do this by putting between L and K a simple algebraic extension. For that we know that there is an extension of this isomorphism, and this gives us the induction step. So if the degree is positive, and f was the, after all, the splitting field, it must be that that f contains a factor which is irreducible, because and of positive degree, of degree bigger than 1. So then f contains an irreducible factor of, say, which I call over K of degree of G is bigger than 1. Because if all irreducible factors of G would have degree 1, then this would mean f splits into linear factors, and so the splitting field of this polynomial would just be K. So thus, we have this small phi is an isomorphism, so thus G hat star G is an irreducible factor of f hat with the same degree. equals to the degree of G. Get them? So now we take a 0 of this thing. So let A be a 0 of G in L. No? So if it's a splitting field of our F, it must also be also all the factors of F must split into linear factors. And prime is 0 of G hat in L prime. Then, according to our theorem about the extension of field homomorphisms to simple algebraic extensions, there is an extension of our original phi to an isomorphism from K of A to K prime of A prime. So then, actually unique, but it doesn't matter now, an extension. Say phi prime from K prime prime of A prime. Obviously, on K, it is just the original phi. So in phi prime restricted to K. So, and now this gives us the induction step, because clearly we have the degree of L over Ka is smaller than the degree of L over K, because the degree of Ka over K is bigger than 1, because A is not in K. So by induction, there exists an extension to an isomorphism from L to L prime of phi prime with restricted to Ka is equal to phi prime from Ka to K prime of A prime, and thus restricted to K is equal to. Okay, so this was quite simple induction. We just used the result on simple algebraic extensions to get some intermediate step here and reduce the degree, and so then induction works. And so that is the result, but we obviously we haven't taken very much care to see how many such extensions might exist. Okay, so this was this result. So much for we will use this result quite a bit. Because after all, we do Galois theory, and Galois theory is is trying to study field extensions in terms of the group of K automorphisms of the bigger field over the smaller field. And so obviously one has to have some means to understand what these are. So now the next step, we get closer to Galois theory, and so in Galois theory we study so-called Galois extensions. one wants to, for instance, understand what all the intermediate fields of a Galois extensions are in terms of this Galois group, which is the group of automorphisms of the big field over the small field. And a Galois extension, so Galois extension is an extension which has two properties. One is being normal, that we will study first, and second, that it's separable, study next. So in a moment I give the definition of a normal field extension, which is not very intuitive, but at least for finite extensions, an extension is normal if and only if the bigger field is the splitting field of a polynomial with coefficients in the smaller field. So there's a simple criterion. And, well, then we come to the separable ones. So let me first write a definition, which is a little bit less intuitive. So an algebraic field extension the L over K is called normal if the following holds. So if every irreducible polynomial say f with coefficients in the smaller field, which has a 0 in the bigger field, already splits over the bigger field into linear factors. Maybe slightly easier to understand, although obviously the same statement is, this is equivalent to saying the minimal polynomial every element A in L splits over L. So this is equivalent because if you have an irreducible polynomial with a 0 in A, with a 0 in L, it is up to kind of dividing by the leading coefficient. It's the minimal polynomial of this element. Okay, so this is yeah, it's a slightly, so in other words, but you could say, so if you have an irreducible polynomial with coefficients in the smaller field, which has 1, 0, then it must, in the bigger field, already all its zeros must lie in the bigger field. So it's a somewhat strange condition. From the definition, it's a priori not clear whether such a thing even exists, because it seems difficult to satisfy that. But now we will see that, in fact, being a normal extension is the same as the larger field being the splitting field of a polynomial with coefficients in the smaller field. So to have it. Yeah, I mean, maybe first, simple example. What is not normal? So, example. So, if I take the extension q third root of 2 over q, this is not normal. Because if I take x to the 3 minus 2, this is a coefficient with this is a polynomial with coefficient in q. This has a 0 in q third root of 2. But it doesn't split into linear factors, because the other zeros would be zeta times third root of 2 and zeta squared third root of 2, where zeta is a third root of unity, so a to the 2 pi I divided by 3. Okay. So now let's do this proposition. So in particular, we see that normal extensions indeed exist. So a finite extension L over K is normal if and only if L is the splitting field of a polynomial with coefficients in K. Okay, so this is, I mean, the proof is not particularly difficult, but it's actually maybe somewhat surprising, because one doesn't really see. So what it says is that, in some sense, we just need to split one polynomial into linear factors, then all polynomials which are irreducible and have a 0 in this field already split into linear factors. That's a somewhat surprising fact. So now let's prove it. And for the proof, we will use this theorem I just wiped out about extension of field isomorphisms to splitting fields in a somewhat slightly surprising way. So we do this direction, which is the non-trivial direction. The other direction is easy, but this is where we have to think. So let L be a splitting field of a polynomial f in Kx. So now let G be a polynomial with coefficients in K and is 0 alpha in L. Now we have to show that G splits into linear factors over L, so that all the zeros that G, for instance, so that all its zeros will already lie in L. So let beta be 0 of G in an extension of L to show beta is an element. So this shows that G will split into linear factors. We can just keep dividing by x minus beta, get a polynomial of lower degree until it splits. So then proposition by induction. I forgot, obviously, one point. So like this, it would actually be wrong, because this is not the assumption of being normal. To have a normal extension, the statement is that every polynomial which is irreducible, which I forgot to write, and has a 0 in L does this. So G should be irreducible. With a 0 in L, then it splits. Okay. So G now we again use first the extension of field isomorphisms to simple algebraic extensions. So G is irreducible. So up to multiplying by a constant, it's the minimal polynomial of alpha over k, and it's also the minimal polynomial of beta over k. Thus, up to multiplying constant, just the leading coefficient, G is the minimal polynomial of alpha and beta over k. So thus, there, by the extension of field isomorphisms, there exists an isomorphism sending alpha to beta. So thus it follows there exists a k isomorphism P from k alpha to k beta. The phi of alpha is equal to beta. I mean, in the moment don't need that, but I need that these two are isomorphic. So L is a splitting field of this polynomial. So L is also a splitting field of the same polynomial f over k alpha. Because we know if L is a splitting field of a certain polynomial with coefficients in k, then it will also be a splitting field of the same polynomial over any intermediate field. And so this is an intermediate field. And in the same way, L beta is also the splitting field of f over over k beta. Because f splits over L into linear factors, but obviously if it's supposed to be the splitting field over k beta, then it must contain beta. So it must contain the smallest field which contains L and beta, which is L beta. So by definition, L beta is the splitting field of these two. And now this will lead to our conclusion, because these two fields are isomorphic, and we have these two different splitting fields. So we can extend this isomorphism to these splitting fields, so it means these two fields will be isomorphic, and this will imply that beta is in L. Okay, let's do it. So thus isomorphism by the extension to field isomorphism. So splitting fields from phi from L to L beta with restricted to K alpha in particular K is the identity of K. That means phi K isomorphism. So we have these two fields are K isomorphic, so they are also isomorphic as K vector spaces. So it follows. So thus degree of L over K, the degree of L beta over K. And so the degree of L beta over L will be equal to 1, which means that L beta is equal to L. Okay, so that means beta is in L. And we are done. So we have found that if I have G, an irreducible polynomial with a 0 in L, then every other 0 in an extension of L will also lie there, and so it will split into linear factors. Now we have to still do the converse, which is easy. Just use a definition. So let L over K be a finite normal extension. As it's a finite extension, we can obtain it by adding finitely many algebraic elements. So we can write L equal K A1 to AN, where the AI are algebraic over K. So let Fi be the minimal polynomial of AI over K, and we put F to be the product of all the Fi. Then I claim that L is a splitting field. So as L over K is normal, Fi splits over L into linear factors. And so also F does. also F splits. And as 1 to n are all zeros of F, a splitting field must contain them, so we have that L of F. So this just was done by using definitions. Here we use these extension of field isomorphisms in a slightly non-obvious way. So now, so this is as much as I wanted to, for the moment, to say about normal extensions. So we have the definition, and then we have this criterion that they are splitting fields. And now we come to separable extensions, which is the other condition for being a Galois extension. So separable extensions. So if you have if F is a polynomial, X, and it will somehow split over some extension. So F can be written as B times X minus A1 until times X minus AN. So splitting over an extension L of K. Now, okay, so that's what we have. Now it turns out that it can cause problems if there are multiple zeros. So if, you know, one of these factors comes with higher multiplicity. So if one wants to exclude this from happening, so avoid the difficulties coming from multiple zeros, one has to say that under certain conditions they won't be there. And the condition which ensures this will be that the field extension is separable. So let me first say what a multiple zero is, a definition. So let F in Kx, that we can write F equal to B times X minus A1 to the M1 times X minus AN Mn with Mi positive integers. So this is a splitting for an extension of L. L of K. So where the Mi are bigger than 0 and the Ai are distinct. Okay, so I have precisely see how often one root occurs. So if Mi is equal to 1, Ai is called a simple root. And if Mi is bigger than 1, Ai is called a multiple root. Of F. Okay, so in some sense, a multiple root means that the polynomial vanishes to higher order at Ai. And now separable is a condition so that for certain, in some sense, a little bit similar to normal, if you have an irreducible polynomial, coefficients in K, has a 0 over the bigger field of an extension, then the extension is called separable if under these circumstances always this polynomial has no multiple roots in its splitting field. So the definition, again, in writing, algebraic extension L over K called separable if every irreducible polynomial f in X 0 in L has no multiple roots in its splitting field. Again, like in the case of normal, we can also say that this is equivalent to saying that minimal polynomial of every element A in L has no multiple roots in its splitting field. So this is maybe even slightly more complicated as a statement, as a definition than that for normal, because we also have the splitting field. It's not no multiple roots in L, but no multiple roots in the splitting field. But anyway, that's what it is. So in a moment we will, so again, it's not obvious at all whether separable field extensions even should exist. But we will see in a moment that actually, for instance, if we are in characteristic 0, all field extensions are separable. So under, so to speak, reasonable assumptions, this is not really a condition. This will always be the case. So in order to study this question, obviously, we have to, maybe I can first just introduce a couple more words. I don't know precisely why things are called like that, but this is the standard word. So if every algebraic extension with K every algebraic extension L over K of a field K is separable, then K is perfect. So as I said, one of the things that we will prove later that every field of characteristic 0 is perfect. Something which we will not prove is that also every finite field is perfect. That's a different statement, but it's not true that all fields are perfect. There are some extensions of finite fields which will not be perfect. Some non-algebraic extension of finite fields. Okay, so now in order to study this condition of being separable, as it has to do with multiple roots, we have to somehow find a way to study multiple roots. And this we do like one does it in analysis. You know that number A is a multiple root of a polynomial if and only if the polynomial vanishes there and the first derivative vanishes. And so we will use the same kind of argument here, where we introduce the derivative just formally by the formula that you have for the derivative of a polynomial. And then, however, the same statement will hold, and that will allow us to study this. So we need a criterion for multiple roots. And obviously, the criterion will be that f of A is equal to 0, is equal to f prime of A, where f prime is the derivative. The criterion from calculus. So let's do this in our context. So what is the derivative? Just write down the formula. So let f equal sum I equal 0 and ai x to the I, polynomial say with coefficients a. Derivative of f is f prime. Well, it's just I just apply the formula that everybody knows and make it the definition. Sum I equals, say, 1 to n I times I times x to the I minus 1. So that's called derivative. You check immediately that this derivative is linear, so the sum of the derivatives, the derivative of the sum is sum of the derivatives, and that you have the Leibniz rule. So you check me that, so if I have AF plus prime is equal to AF prime plus BG prime, where F and G are polynomials, A and B are numbers in K. So its derivative is linear, and if I take the derivative of a product, again, F and G are now polynomials, this is equal to F prime G plus F G prime. So that's an easy exercise, just by, everybody can prove this from this definition. That's some exercise for high school or whatever. So and now we can check this criterion. So if I have a non-constant polynomial, and say L over K, the splitting field of F, and say A element in L, then A is a multiple root of F if and only if f of A is equal to 0 and f prime of A is also equal to 0. And by these rules, this follows essentially so R be of A as a root. So then we have that F is equal to X minus A to the R times G with of A. All right, if I take the derivative, then F prime, I apply the Leibniz rule, and if you deductively here, you obviously see that the derivative of this is R times X minus A R minus 1. Okay, so anyway, if R would be equal to 0, this doesn't matter, so I can assume it's positive. So, so you see that this term is 0 at so this term will always be 0 at A because it's divisible by this, and this term will be 0 if and only if R is bigger than 1. So thus F of A is equal to F prime of A to 0 if and only if R is bigger than 1. So if R is 0, then anyway F of A is not 0. And if R is equal to 1, then this will be 0, and this one will not be 0 because here G of A is non-zero, and this term, however, is 0 at A. And so that's it. Okay. So now we want to deduce from that, for instance, in characteristic 0, being separable is no, I think it's written with an A. Being separable is no condition. So we have the following theorem. First says, so let F in Kx be irreducible. So then F has no multiple roots in its splitting field if and only if F is not 0. F is not the 0 polynomial, the constant polynomial 0. So it's not 0. F prime is not 0. That's what I mean. Okay. So you see that's, so all of a sudden it becomes a very strong condition. So it can only be multiple root, F can only have a multiple root if the derivative is 0 everywhere. And for instance, in characteristic 0, you can see that this is impossible unless the polynomial is constant. and then irreducible, so that cannot happen. So we look at the splitting field, that L over K is splitting. I mean, this is a little bit surprising maybe, because it doesn't seem like this is such a strong condition to have no multiple roots. But the point is that if f is irreducible, you could view it as a minimal polynomial. I mean, up to multiplying by a constant, it's the minimal polynomial of any of its zeros. And if both f and its derivative vanish there, then according to the definition of minimal polynomial, it must be that the derivative is a multiple of f. And that will be impossible unless the derivative is 0. So it comes from this irreducibility is very important. So if f prime is a 0 polynomial, then by definition, every 0 of f is a multiple root. Not by definition, but by this criterion, is a multiple root. Okay, so now the other direction. So let A in L be a multiple root. Of f. Then of A is equal to f prime of A. 0. So as f is irreducible, up to multiplying by constant, f is the minimal polynomial of A over K. So, but we know that that means every polynomial which vanishes at A is a multiple of f. Thus, f divides f prime. But this is impossible. So, but if f prime is not the 0 polynomial, this is impossible. Because by definition, the degree of the derivative is smaller than the degree of f. It can obviously not be that a polynomial of bigger degree divides a polynomial of smaller degree, but obviously every polynomial by definition divides the 0 polynomial. So that's okay. And that's the proof. So now you might think that that shows that you never, that field extensions always have to be separable. If you have an irreducible polynomial, it can, under no circumstances, have a multiple root in its splitting field. But that's not quite true, because this condition that the derivative is 0 can happen if the characteristic is P. So for instance, in FP, we have that if we take, for instance, x to the whatever, 2p minus x to the p, if I take the derivative, this is the 0 polynomial, because p is equal to 0. So in that sense, you can, this condition can happen if the characteristic is p, but in characteristic 0, obviously it cannot happen. The derivative of a non-zero polynomial, by definition, is never 0, because if you write this thing down, you can see what the coefficients are. So if you have a non-constant polynomial, these ai are non-zero. You multiply them by the number I, this will not be 0. So therefore, get as a corollary every field characteristic 0. Where perfect is a state that every algebraic extension of K is separable. So now we come to an important and not so easy theorem that we want to prove about separable extensions. The theorem of the primitive element. So this is so we had seen that simple algebraic extensions can be understood quite easily. On the other hand, I had claimed that under reasonable assumptions, all finite algebraic extensions are simple algebraic extensions. And that's the theorem of the primitive element, which says if you have a finite separable extension, then it is a simple extension. So it can be obtained by just adding one algebraic element. And so now we want to try to prove that. And that's very useful for us because then, we can always use what we know about simple algebraic extensions, which are so much easier to understand. So we have the theorem. So the theorem, the statement is the following. So let L over K be a finite separable extension then there exists an element A in L with L being AA. Okay. So, and this A you would call a primitive element. So one element which generates the whole field extension. And so the claim is that every finite separable field extension has a primitive element. Okay, so this is clearly, this somehow cannot be easy because it's not at all clear where this A should come from. I mean, how would you find it? And so we will have to work. So first I will cheat a little bit. I will assume for simplicity that the field K is infinite, has infinitely many elements. So something like Q or whatever, not a finite field. This also works for finite fields, but the proof is more complicated and I will deal with it only in this case. So for simplicity, K is infinite. Some extension of Q or whatever. So as I said, it works also for finite fields, but there's an additional complication which I don't want to go into. So as this is a finite extension, we can obtain it by adding finitely many algebraic elements. So we can write L is equal to A1 to AN for some A1 to AN in L, which are algebraic. So now we want to show that we can make do with only one. So to make our problem a little bit simpler, we start by reducing how many elements we have here by using induction on the number of elements. So some kind of preliminary step. So we make induction over M. So if n is bigger than 2, then we can just look at we can make induction over n. So we leave out the last element. So then we can write by induction that k A1 to AN minus 1 is equal to Ka for some A. K A1 to minus 1. So thus, we obtain our L by just adding one more element. Thus, L is equal to K AN. So by using this induction, we can therefore assume that L is generated by two elements instead of by an arbitrary number of elements. So thus, by induction, we can assume that N is equal to 2. And we have to then show that n is equal to 1. So I change the notation slightly. I write my two generators A and B. So we write L and we have to show that we can make do with one element. So this was maybe the end of the preliminaries. So via this simple induction, we have reduced ourselves to the case that we have only two generators. But now we have to really work to make it. Now such simple methods will not work. We have to really do something to make out of these two only one generator. And so in this case, the answer, however, is a very simple one. We can take linear combinations of A and B with coefficients in K. And the answer is that when we take any such linear combination, all except for a finite number of those will be generators. So we want to show L is equal to KC for C general combination. Say C is equal to A plus Z. So to say it again, we'll show there, find the many choices of Z for which this does not give us a generator. But for all other choices, this thing will generate L over K. So L will be equal to Kc. OK, now we have to see why this might be the case. So we have these elements A and B. So now we have to analyze a little bit. So we look at we eventually will also have to use the story that this is separable. In the moment, we don't see why this has anything to do with anything. And so let's see. So let's look at the minimal polynomial of these two and look at the zeros of this minimal polynomial in some extension of K, of R. So let F be the minimal polynomial of A, K, and G, minimal polynomial of P over K. And now we take an extension where both of them split. So let F over L field extension where both F and G split into linear factors. So we could, for instance, first take the splitting field of F over L. Then F splits there, and then we take over that field, we take the splitting field of G. So over this big field, both F and G split into linear factors, and we keep track of what the zeros of these two polynomials are over this big F. So let first zero is maybe A, 1, x2 until n be the zeros. F in L, in F, large F, and B, y1, m. And now we know that as we have a separable extension, G was irreducible. So we know that all of these are different. So B is, in particular, B is not equal to any of the others. So as L over K is separable, B is different from Yj for all n1. So thus, now we want to solve a certain equation. So let's look at this equation A so we look at the equation A plus ZB equal to xi plus z yj. So we look at these equations for for I equals 1 to n, j equals 2 m. So now you see B is different from yj. So we can just solve it. So this has a unique solution. Just doing a simple linear transformation. We bring the xi's on one side, the things with z on the other side, and we divide. So zij. So the solution for this choice of I and j is zij equal to xi minus a divided by b minus yj. No? Bring this over, we divide by b minus ij, we get this. So given, for any given I and j, there's a unique such solution. So maybe I write here just Cij to make it clear. There's a unique solution like this. So, and in particular, so we have the Cij for I equal 1 to n, for j equal 2 to m. So altogether there are whatever less than n times m elements. And so if we can certainly, as our field is infinite, we can choose an element z in K, which is different from all of them. So as K is infinite, there is an element we can choose, an element z in K, which is different from all zij. For all I equal 1 to n, j equal to m. And then obviously this means that if we put this z here, then this identity will never hold for no I and no j. So thus A plus bz is different from xi plus z yj unless I is equal to 1. In which case A is by definition equal to x1 and B is equal to y1. So then it obviously trivially holds, but otherwise it never holds. Okay. And now the claim is that this thing does. If we put equal to A plus BZ for this choice of Z, and the claim is that KAB so clearly, that's anyway clear, we have that KC is contained in KAB. Because after all, Z is an element in K, so this is just a linear combination of A and B with coefficients in K. It certainly lies in KAB. So this is the trivial direction, and we have to show the other direction. This is the more difficult part. So KAB is contained in KC. So now we will wait, maybe. Okay, maybe I do it here. So we will want to show this by showing that we can express B as an element in KC. And in fact, we will want to show that X minus B is a polynomial with coefficients in KC, which is the same. And this we show by showing that it's the greatest common divisor of two polynomials with coefficients in KC. So let's see. So first, we do something a little bit more crazy. There's a trick. So we define a polynomial H, coefficients in KC, by putting H of X to be f of C minus Z times X. Okay. So we have designed it in such a way that, you know, what, if we look at it, if we put B into this thing, we get C minus Bx, and C minus Bx is minus Bz, and according to this, so as equal to A plus Bz, we have that H of B equal to f of C minus Bz, which is f of A. And f was the minimum polynomial of A over K, so A is the 0 of it. So we have that B is the 0 of f. So 0 of f of G. So B we know is a 0 of G in F. F and also of H. So thus means that X minus B will divide H, and it also divides G. So thus X minus B is a common divisor of H and G. And now the claim we make, claim will prove it, is that it is a greatest common divisor. I write it out, greatest common divisor. Of H and G in Fx. Okay. Now, yeah. Or maybe also, I think I can even take it in Lx, because B lies. Anyway, doesn't matter. No, but I do it in Fx. Okay, so first let me see why with this I get the theorem. So theorem follows from claim. So we have, by definition, we have that H are both elements polynomials with coefficients. G was actually a polynomial with coefficients in K, and H, by its definition, is a polynomial in Kc of X. So, and okay, so we had this corollary to the Euclidean algorithm, which said that if you have a greatest common divisor of two polynomials with coefficients in a certain field, which is, for instance, monic, so the leading coefficient also lies in this field, then the whole polynomial lies in this field. So as so x minus b is a monic, a greatest common divisor of h and g. X by the Euclidean algorithm we got as a corollary of that x minus b is an element in of x. So it's just the trick was just that if you a greatest common divisor can be obtained by repeatedly applying the Euclidean algorithm, I mean the division with rest, and by this the field doesn't get bigger, so you get one candidate for the greatest common divisor by the Euclidean algorithm inside Kc of x, as these two polynomials are in Kc of x, and to check whether, as the greatest common divisor is well defined up to multiplying by a constant, if the leading coefficient lies in this field Kc, in this case it's 1, it certainly lies in Kc, then the whole polynomial lies there. So this lies in Kc of x, so thus is an element in Kc. And now we are done because by our equation we have thus we have that A is equal to C, is it subtract minus E with Z and K, so thus also A is in Kc, so thus contained in Kc, and we are done. Okay, so now we have, the only thing we have to do is to prove this claim. And that's not so difficult now because we have chosen things the right way. Do I need this? Okay, let me do this. So proof of the claim. So G splits over F F into linear factors. It was a minimal polynomial, so it was monic, so we can write G is equal to x minus y1 times and so on times x minus ym. Thus, up to multiplying by a constant, a greatest common divisor of P and H must be a product of some of these. No? If you have a greatest common divisor, it's again a polynomial, so it's zeros, this will also split into linear factors, and they must be some of these linear factors. So must product sum of the x minus yj. And now what one wants to claim obviously is that h is not divisible by x minus yj for any j different from 1. So when yj is not equal to b, then it does not divide it. So, and this is basically by our definition. Unfortunately, I did wipe it out, but okay. So for j different from 1, that means yj is different from b, here we have h of yj is by definition f of c minus z times yj. And I claim this is not 0. And this is because by the choice, we have that c minus yj is different from xi for all roots xi of f. No, because we had that, note that it's written there, c is equal to a plus b z. So c minus z yj so this will be so if I bring it over, this is plus b z minus z j. And this, according to this, according to this formula, this is different from xi for all I from unless I is equal to j is equal to 1, which is precisely what we have here. So this is precisely written here. So we see that this is different for all other roots. So if yj is different, if j is different from 1, then this will not be 0, h of j will not be 0. So the only 0 among the zeros of j, or of g, that h has is b. So the greatest common divisor is x minus a, x minus b. Only among vectors x minus yj. That divides. X minus b is a greatest common divisor of G and H. And so the claim is proven, and thus the theorem. So the greatest common divisor in Fx. If I have the greatest common divisor in Fx, then we know it lies in Kc, so B lies in Kc. Okay, so maybe that's enough here. I'm sorry I went a little bit over, but I couldn't very well stop this proof in the middle. So are there comments or questions? Otherwise, apparently not. So I think I will try to make some homework today, and otherwise we will see each other for the next lecture on Friday, and on Thursday, as I said, we will meet to discuss about applications for PhDs. I will also send you an email. I think it will be confirmed 11 a.m. on Thursday that we meet on Zoom for this. Okay, thank you very much, and have a nice evening.
Thank you.